Good morning, everyone. Hope you all can hear me okay. Couple housekeeping things. We're going to start here any second. Hoping you all can hear me well. Anybody wants to throw a note into chat, tell me that. That'd be awesome.
We can hear you.
Oh, thank you very much. Awesome. So what we're going to do is we're going to ask that you all mute your microphones. There's going to looks to be a lot of us on the call, 68, almost 70. And that just adds some background noise that probably don't need. As we progress through the slides, we ask you to put your questions into the chat box. There's going to be several of us watching, and we can answer those. Between the staff of XSEDE, we may choose to answer them verbally so everybody can hear us, or there might be a few that we'll answer through chat. So we're going to sort of mix it up there a little bit. Let me go ahead and get started. Let me do some introductions here. We have a couple XSEDE staff members that have worked to put this together, predominantly the extended collaborative support team that's built up from the different partner sites of XSEDE. Jay Alameda, who heads up the ECSS staff for training. He's sort of our wizard behind the curtain here. So thank you, Jay, for helping us with this. Our other presenter today is Lars Kosticki from the Texas Advanced Computational Center. He's going to do the details of the actual code performance and scaling. So Lars, thank you very much for joining us, and we look forward to your presentation. And myself, I'm Ken Hackworth. I oversee all of the allocations for the XSEDE program. Some of you probably chatted with me, or we've exchanged email or tickets or something like that, or you maybe were on some of my webinars that I hold twice every quarter. So our topic today is training with code performance and scaling, with really the focus is for XSEDE research requests, which code performance and scaling is a mandatory document so that the review panel has a good understanding that you have tested and tried these codes and can make efficient use of these. So I apologize, you might hear some dogs in the background drinking. Apologize. All right, so let's go ahead and get started. I'm going to share my full screen, and as we go, if you have questions, put them in the chat box, and we will go ahead and answer those. Okay. Slide. So as with any XSEDE function, we want to make sure that you're aware of the code of conduct. I know that you all, to register for the function, there was a box you had to check off that you understood this. But again, we just want to make you aware of this, that we are an institution that we just want to play fair, everybody be comfortable, and all. If you have questions or concerns, you can always reach out to XSEDE. I'm as one of the ombudsmen for this. So if you have questions or concerns, you can always send me an email or any of the others that are listed there. So with that said, let's have a great webinar. So the XSEDE mission, and I don't really have to read it, but I will, to substantially enhance the productivity of a growing community of scholars, researchers, and engineers who have access to advanced digital services that support open research and coordinate and add significant value to the leading cyber infrastructure resources funded by the NSF and other agencies. So we're here to do great science, and we have resources that can help you do this great science. These digital services provides users with seamless integration with NSF high performance computing and data resources. You're all probably aware that there's many resources that we have. So some of those resources, which is a diverse portfolio that are allocatable, if that's correct. So we have HPC systems, we have high throughput systems, GPU and AI systems, visualization and data analysis systems, large memory systems, data storage, cloud systems. And then we have XSEDE staff, us that are going to be doing this talk. That's ECSS and the SGI, Science Gateway Initiative. software daily. So, but again, I think all these resources are great, but our staff is really great. We're here to help you. So that's why we're going to do this talk. And if you do find that you need help along the way with anything, we are always here to help you. So a little bit about the eligibility. So most US-based researchers are eligible for these no-cost allocations via XSEDE. Startup allocations, we can get these started fairly quickly for you. It's pretty minimal request. We can usually do these in less than 2 weeks, usually a few days. The main focus of this webinar are these large production allocations, which we refer to as research allocations. These can be requested yearly with available submission period every 3 months. And we're currently in one of those submission periods, which will end on April 15th. Why request a startup allocation and how to get one? These are requests can be accepted anytime. There's no deadlines. They're reviewed in less than 2 weeks. These multiple resources can be requested. The whole portfolio of XSEDE allocated resources are available through startups. To be eligible, the eligible PI with a CV and an extended abstract is really all that's needed for a submission. What's the purpose of startup allocations? These are small-scale computational activities, application development, evaluation and experimentation on the various resources, benchmarking. And here I put in big letters, bold and red, code performance and scaling. And that's why we're all here together. So using your startup allocation to test and benchmark and get these performance information that you're going to need if you are going to graduate to a research allocation. And again, a code performance and scaling document is necessary. Research allocations, these are for projects that have progressed beyond the startup phase. You can ask for really any amount of service units that you would need. Let me step back. Service units is a measure that we use, or a unit that all the sites use. But different sites have different measurements for a service unit. Some may be core hours, some may be node hours, some may be GPU hours, some may be memory hours, some may be VM hours. So there's a variety of service units, the way the sites calculate them. So we use it just as service units, sort of pretty vanilla there. So these research requests that we're going to mostly talk about today, they're reviewed quarterly by an extract panel of peer reviewers. We really recommend 1 award per PI or research team. This is a highly competitive process. We see greater than 200 proposals per quarter. That's actually a low number. We've seen as high as 275 at meetings. So again, it's very highly competitive, and that's why we're here to make sure that we can help you get over that hump with a good code performance and scaling document. Proposal quality matters. There are lengthy proposals, but we're really looking for a well-written proposal that has taken the time to do things correctly. We award around 80%, maybe a little bit more, a little bit less, but that's a number we're shooting for a little bit higher. But the ones that are declined are poor code and scaling information. We checked in the past year of proposals that were declined. 30% of the new requests that were rejected was because poor code performance and scaling information. So that's why we are here. At this time, I am going to hand off the webinar to Lars. I'm going to unshare, and Lars can share his so he can drive his slides. Again, hopefully this will be a good session for y'all. And if you have questions, put them into the chat session, and we can proceed from here. All right, Lars, it's all yours.
Yes, thank you very much. Okay, sharing my screen. I think you should see my screen now. Yeah, so I'm going to go into some of the details of what a good proposals will be. there's a lot of general advice that applies to every or any proposal that you submit. And then I go into some of the details for computational requests. Those are most of the requests that we get there for computation. And in this slide deck and in this presentation, at some point we will add some specific stuff that addresses other areas that are important, like AI, things like that. But for now, the details that I have are just for the computational requests, but a lot of this stuff applies for to any proposal. So if you write a good proposal, a successful proposal, it's always the same thing. You have to know your audience. And here, the audience are reviewers who want to know what your computational plan is, and they want to know and they want to be assured that you know what you are doing and that you are using these resources efficiently and effectively. These resources are expensive. Smaller ones are 10 million, larger ones are 30 million. So there's a lot of money on the line. And of course, you want to do science, and the science is important, but that's not what the reviewers will focus on. Most of you have funded projects, and when you submit an XSEDE proposal and you have funded science that is backing that up, then your science is not really reviewed. Nevertheless, your computations should be, of course, matching the science that you want to do. So what is most important is that you demonstrate that you are competent to use these expensive resources. And although you do not know yet, from this talk at least, what a good proposal is, you know already what your proposal is not. It is not an NSF proposal with just 2 sentences presenting a number of service units that you think you need to do your science. That is absolutely not what you need to do. On my next slide, I'm just repeating the startup thing. You can review that later. Ken went into a lot of detail. But once you go from a startup to a full proposal, you have to always apply some common sense when writing your proposal. There are just a few facts of life that you just cannot avoid. If a request comes in from a new group, you are under more scrutiny than if it is a proposal from a well-established group. Well-established groups have a better chance of winning very large awards, of course. If you're a new PI, you have to establish some kind of a track record first. And then most importantly is you have to get some grip on how much time you're actually asking for. And there is no hard guideline, but at least what you can do is you can figure out how many SUs are available on a given resource. You know the number of available nodes that you get from the manual or from some guidelines. You know how many hours are in a year, and you know how much time you want to ask for. So you have to limit yourself to a reasonable fraction of the targeted system. If you go, it's a little bit different for smaller systems and for larger systems, but if you ask time on a large system in XSEDE and you are asking for 10% of all the available SUs, then you know you're already in a regime where the air is very, very rare, and where you basically, as a new PI, have no chance of winning 10% of a large resource in XSEDE. There are thousands of researchers on groups who use these resources, so you have to apply some common sense first to this. Another fact is, of course, that smaller requests face less scrutiny than larger requests. And what you should also keep in mind is focus on what you really need. If you only want to do compute, target one resources. Do not target several similar resources without a good reason. So don't say, hey, I want to use a cluster in California, and I want to use a cluster in Pittsburgh, and I want to use a cluster in Texas, without any reason why you need three resources that are very similar. Of course, if you want to you want to do compute and you need a cluster for that, and you want to do some AI and you need a different resource, that is perfectly fine. But don't just go and ask for all the resources that you see on the availability list. So my hands-on advice is use common sense when preparing your proposal, pick a reasonable request size, acknowledge internally that there is a fierce competition for these resources, so writing a better proposal really pays off. Overly ambitious proposals from new PIs do not really fare well. On the other hand, also keep in mind that when you are rejected, you can resubmit your proposal 3 months later. So there's really not that much time that you lose. So being rejected is not such a disaster. But if you write a good proposal to begin with, then you're just much better off. So what makes a good proposal? So on the left, I have a basic outline of what your proposal may look like. You describe a little bit of the science, you describe the specific scientific questions that you want to answer. You go into a little bit of detail of what software you want to use, how the software is parallelized. Maybe you should always throw in if you're experienced with using this software, things like that. And then points 4 and 5, those are the most important parts. Computational plan, and then a realistic and reliable estimate of the service units that you are asking for. I forgot to do the chat room thing. I want to monitor the chat room in the background as well, if there are questions for me. And so back to the basic outline, you want to also provide supporting data, scaling that documents your computational efficiency of your, it should say, code. And so in the details, your proposal is somewhat similar to an NSF proposal or to a proposal that you send to a funding agency, but not all of your reviewers are necessarily domain experts. They are all experts in computational, in high performance computing computations, but they're not all domain experts. So a little bit of a broader approach is appreciated by the reviewers. And of course, you don't have to go into that much of a detail that you go in your NSF proposal, because you're not justifying the science you want to do. And so next step is you connect your scientific questions to the computations that you are proposing. So there should be a connection. I'm working on this scientific question, and these are my computations that I think will help me answer these questions. You should. Oh yeah, there's a question. Yeah, we will have access to the PowerPoint presentation later. Yes, I think so. Jay or Ken will distribute it, or they can already distribute it while I'm giving the talk. You should go a little bit into some detail about what equations are being solved and how the code is being parallelized. I mean, that doesn't mean that you present the equations, but that you get the reviewer some idea of what you are doing. And I have a good point about that later. You know, if you have done anything to increase performance, there's always a good time to brag about what you have done, and reviewers appreciate it very much. But the basic point is that you assure the reviewers that you know how to run the code and that you understand how this all works. And then you present a computational plan that details the number of calculations that you want to do, the total runtime, and also the node count. And when you do that, you use basic math to allow reviewers to verify your total SU estimate. And I'll go into some more details later on. But the idea is that you're not losing the reviewer with a sentence like, and therefore we request. There has to be some basic math. We want to do 5 calculations. Each calculation takes such time on so many nodes, and so on and so on. And then oh yes, there's commercial software and community code software. There's a question in the chat room. I will address that too? And the quick answer is yes, you have to show scaling as well. The equations, I mean, if you use a community code or like molecular dynamics or stuff like that, no, you don't have to explain the equations. So back to point 6. You will use the scaling data to prove and show to the reviewer that you are efficiently using the resource. And then you justify the size for an individual calculation based on your scaling efficiency, total runtime, and your reviewers will appreciate all efforts that you will document. Yeah, there's another question. Yes, I will address a little bit about time step information and how this all works, I hope. So my hands-on advice is the computational plan takes center stage, and therefore your computational plan is not just a terse sentence and therefore we request X million SUs on that resource. Reviewers want to be assured that you know what you're doing, and they want to be able to follow your math, how you come up with how much SUs you really need. So now this is the weirdest part of the review process. It is, of course, very difficult to judge efficiency of an application. You can always argue, you could do the same thing with a different algorithm or stuff like that. That is, unfortunately or fortunately, beyond the scope of what you have to show, because that is an open-ended question. But the review panel will be using your scaling efficiency as a proxy to judge the efficiency of what you will be doing. And the reviewers will then like to see scaling on the target system or a very similar XSEDE system. So it's not enough to just say, hey, I run it on my cluster at my university, and now I transfer my results, my scaling directly to the system without showing what that really means. So you have to use your startup allocation to document some scaling on the targeted system. And for the scaling efficiency, the scaling will also be used later on for the second part of your core pieces of your proposal. But what you will do is you present scaling for a typical case. So you present timings for a few time steps or timings for a smaller sample. Of course, some situations are more complicated. If you have adaptive mesh refinement, you choose a simplified setup, discuss a little bit the implications. But the documented scaling should cover the nodes targeted for production or for large runs where that is not possible. You apply a well-justified extrapolation from a smaller sample. So for example, for a smaller sample, you provide the scaling up to a certain number of nodes. And then you say, my real computation now is 8 times as complicated. With complicated, I mean, it has 8 times as many particles, or the resolution is 8 times higher. And now you say, hey, now I extrapolate from my code with that I'm showing with my smaller sample scales well to 128 nodes. Now I made my sample size 8 times larger, or my resolution 8 times larger. So I expect I get the same scaling on 8 times as many nodes, and then you extrapolate your compute time and your request from there. Oh yes, there's a question, of course, about what is a good scaling analysis, and that will come in a couple of slides. And of course, what reviewers want to see is that once you have established a scaling curve, that you will pick a number that for node count or core count, that is a good number, and where you balance wall clock time and scaling efficiency. And so we come to the first scaling plot, and whenever you do scaling, there are 2 kinds of scaling. There's strong scaling and there's weak scaling. A strong scaling is easier to understand, but you keep the amount of work fixed, and now you throw more and more resources at your problem. And when you do that, you get a better, you get a speed up. And on the right side, the straight blue line, that is of course ideal scaling. You use twice as many cores, you get a speed up of 2, or your execution time decreases by a factor of 2. Now, your real world scaling is here the orange line, and of course, at some point, the scaling will be not so good. You will reach a maximum, and once you hit the maximum, your scaling will even decline because there's overhead and all these kind of things. But the first point to take away from here is that do not pick the maximum speed where your wall clock time is the shortest, because at that point you have already very, very low efficiency. And so you present your scaling, and you will pick either in the green regime or in the orange regime, and you make your case from there. The other important, there's a question about high throughput computing jobs, and maybe I will address that later. I write it down here on my notepad that I will that I have to address that. So the other point from this scaling plot is that you have to present your data in a way where the reviewer can easily judge what your scaling is. So here I'm presenting speed up and not execution time. Execution time would be 1 over x, and your ideal scaling is then a curve. I have that on the next slide. But here, when I present speed up, then everything is linear if you use a linear axis for both axes, or if you use a log-log diagram. So then it is easy to judge for the reviewer. If you do execution time, then you have basically a 1 over x plot on the right side, and there it is hard to see if your scaling is good or scaling is not so good. I'm pretty sure you all have been reviewers in during your career, and you know how a review process works. The reviewers are judgmental, that is their job. And the reviewers may reject just your proposal if it takes too much time or effort for them to make sense of your data, you know. And if your data could be perfectly fine, but it becomes too convoluted for the reviewer to disentangle what you are presenting there. And then at some point, reviewers may become suspicious that you are presenting your data in a certain way to hide that your scaling is not as good as it should be, or more importantly, that you're selecting a higher number of nodes than you should, and that you're trying to hide that fact a little bit. So once a reviewer becomes suspicious of that, he or she will reject your proposal and ask you, hey, come back in 3 months and explain it better. And by being transparent, you can avoid all that right from the get-go. The other scaling is weak scaling. In weak scaling, you keep the amount of work scales with the number of cores or nodes, or the amount of resources that you will use for your computation. So that means that your execution time is constant and equal to the time on a single node or on the smallest number of nodes that you can reasonably use. Usually memory constraints are a factor there. And now your parallel efficiency is the ideal time divided by the actual time. No, it must be the actual time divided by the ideal time. Sorry, that's some basic math error here. But your ideal time is constant, and your actual time. No, it's correct. I'm sorry. Ideal divided by actual. And so your parallel efficiency will look like here on the right-hand side. 1 is your ideal, and then the orange line is your measurements. And now for the x-axis, you can use linear scale or log scale, depending on how far your scaling range, how far your data goes. And you pick good scaling, reasonable scaling, and not the bad scaling. So my hands-on advice is here, use a common sense when you pick a target size for your computations. Particularly for large calculations with a high SU consumption, do not target quick completion at the expense of efficiency. If you are not doing that, then you demonstrate that you will use the resource efficiently, and the review panel is not overly concerned with work log time. Your award period is a year, and you're expected to run through that whole year. So unless you have excellent scaling or you have only a very small allocation, it is expected that you run through the whole year at some kind of even burn rate. But on the other hand, non-ideal scaling is a fact of life. You cannot avoid that. So don't be discouraged if you think, oh, my scaling is not ideal. You just have to find a good compromise and present, of course, your data in a favorable way, yet being transparent so that the reviewer understands what is going on and doesn't feel deceived. But just having non-ideal scaling, that is just what most applications have to live with. Detailed definition of speed up might be helpful. Yes, I mean, for strong scaling, I think that is kind of obvious. The speed up is when you divide the time on multiple nodes by the time on a single node, or the reverse of it, so that you get the linear scale. And for weak scaling, you have the ideal time, that is the time on a single node versus the actual time. Oh yes, there's a question about AI projects. That is something that will come up later. I'm not an expert in AI, and so I do not know how reviewers judge that. So there I cannot help you at the moment. So you find a good compromise and you present your data in a favorable way. Now the scaling, so far we have discussed how you use your scaling to pick a reasonable size for your computation. But there is another reason why you need the scaling data. You have to present some simple math to estimate the total request size. So you use the timing from your scaling experiments, and then if needed, do some reasonable extrapolation towards the number of time steps or the resolution that you want to do. So you give details regarding all planned experiments. You allow the reviewers to easily follow your estimate and give the reviewers reassurance that your estimate is not bloated. When I review proposals, I always appreciate it if there's a table to summarize that summarizes all individual experiments. So I'm basically reading the proposal backwards. I'm reading the table with the summary first. I get an idea of how many experiments there are, and then I read backwards in the computational plan to see how is that all justified. And then for parameter studies, of course, you highlight that you have selected a reasonable or a small number of parameter combinations. So just to have a complete set in the first go around, that is usually not a good argument. And you should always discuss how your first results may inform the selection of other parameter combinations if that is needed. And already to alert you, there are other things than compute. Do not forget to justify storage for all your compute calculations that you have to do. Now we come to community codes and well-known codes, and there scaling for these codes is often well documented, but nevertheless you have to document your own scaling for your own proposal, and there are two reasons for that. You present scaling for your specific setup. Community codes can often do many more things than what you want to do, and so reviewers cannot be sure that for your specific setup, the scaling that they have in mind, that they have read from different publications, will apply. But the most important part is the last bullet here, that you will use your scaling experiments to accurately estimate the request size for your proposal on the machine that you are targeting. So you could argue that if the scaling is well documented, then you just use the scaling that is well documented. But to accurately estimate your request size, you need to run your experiment, and reviewers will look for that. So you are not getting a pass just because you're using a community code. And again, you present scaling for typical case, you use your results to estimate your SU cost, and please do not refer to external documents when you discuss scalings. When I review proposals and there is and here you can look at this widely known a document, I'm not interested in reading more stuff than the 10 pages that you submit in the actual proposal. So whenever you refer to external documents and I'm your reviewer, you're having already a hard time. And of course, reviewers want to read about your experience on a specific system, and that is very important to them. So some additional considerations, and then we can wrap up. You have to add and justify additional requirements. The first one that comes to mind is, of course, is storage, and that can be either long-term on tape or medium-term on disk. And you just have to say how much data you are producing, for how long do you need it for an analysis. And oh, I'm sorry, I got distracted. There was a question in the chat. Let me address the question in a moment. So you ask for storage, and it's the same basic math. You do a number of calculations. Each calculation produces a bunch of output. It will take you to analyze that output. It will take you some time, and you detail that all in your request, and then you shouldn't face any problems there. For some proposals, for some research, there are special queuing demands, and you know, if your research is time sensitive, so for example, you do weather forecast or you do tornado tracking, then you can always add special queuing demands, but that is only for very well justified requests. But it's of course something that we, as the resource providers, we work with users on these special queuing demands every day. Also disclose any problems that you may anticipate. You know, resource providers are happy to work with you before you cause trouble on the problem, on the system. And you're not penalized for disclosing that your code has or it needs some or may cause some trouble IO-wise or other things. So always add your special requirements to the proposal, and we have a whole team of ECSS staff members who can help you with specific problems and help you improve your code or your code performance. Discuss bottlenecks that you may anticipate. So a typical one is IO, where users sometimes overwhelm the file system with the number of requests, things like that. Or if you have a lot of files to be transferred from other resources, and yeah, and whatever you have there. Yes, Scott was asking about the table at the end. Where did I have the table? Yes, so when I review proposals, I review the proposals I read the proposals backwards. I'm not reading the science first and then the scientific question. I'm reading the summary of the request first, and I'm always happy if that is a table. And then it says experiment A will use that many SUs and experiment B will use that many SUs, and the experiments have different computations and the computations are done at a certain node count. And then I go back up, move up in the proposal, and I read about experiment A and how it is justified, and I read about experiment B, how that is justified, and I read the scaling document, and so on and so on. And to be honest, if I'm already satisfied at that point and I kind of have an idea what the science is, then I sometimes don't even read what the science is about. I read a little bit about the scientific question that the PI wants to answer with the calculations, and I make sure that kind of it matches what the experiments are outlined. What experiments are outlined in the summary, and then I'm fine. Of course, I always read a little bit the description of the software. So if it is community code, then I already know what that is, but nevertheless, I always like to read what an individual PI is writing about that software, and then I read all the other stuff. But the science part is really the last part that I read. I read the proposal really from the back end to the back to the front end. Okay, we were here now. Additional considerations, hands-on advice. So I always think that a little bit of bragging goes a long way. So if you understand what your code is, oh, Mark is commenting a little bit sad that the science is somewhat irrelevant to you. Yeah, I mean, I'm not a domain scientist in all the proposals that I get. So often I find the science very interesting that is not in my domain. If the science is in my domain, I mean, my background is physics and astrophysics, then I read, oh, there's another star exploding, or another two neutron stars are colliding. That I find actually less interesting than other science where I can actually learn something about things that are going on. But in the interest of time and efficiency, I always have to focus on what my job is. And my job is to judge computational efficiency and the computational plan. And so that is why I start at the end. And of course, what that also means is, what that also means is that a very short computational plan shows me that this is basically just an NSF proposal where somebody just tacked on a few sentences about a computational plan. Oh, Mark, I'm so sorry that I disappointed you again. I do not know how I can make it up to you. Maybe I can review your proposal next time and do it that way. Okay, so if you have done anything of these, if you have put in some effort to understand your code performance and workflow performance characteristics, if you have profiled your code to measure performance and then did some code optimization or some optimization to improve scaling or to optimize I/O, always write about your efforts. Reviewers are very happy to read about this, and that convinces them that you know what you're doing, that you are interested in optimizing your code, and that you're interested in getting the most science out of the number of SUs that you're getting from XSEDE. And so it always helps to write something about your past efforts. Now maybe I can address a little bit the high throughput computing situation. Yes, if you do high throughput computing, if every time you run your code, every instance is just on a single core, yes, then there's of course no scaling. But nevertheless, you should convince the review panel that you will pack the appropriate number of individual calculations on each node, and so that the cores are not idle. And with appropriate, I mean there are sometimes memory limitations. So if a single instance of your code uses up more memory than is available per core, then of course there has to be some cores idle. But nevertheless, you can argue and you can convince your reviewers that you will make all the efforts to bundle your computations up so that cores are not unnecessarily idle on the nodes. And if the execution time varies from instance to instance, that you will apply some scheduling scheme to always, you know, fill the nodes up with computations. And I can only speak for my center, but I'm sure all centers do that. We all provide tools that allow you to do high throughput computing on multiple nodes, and so everything is already set up for you. Oh, there's a long comment. Let me move this up here a little bit and read this. Oh yes. Yes. Okay. That's a very good point. You have already done the very tedious work of making your MATLAB, converting your MATLAB prototype into a compiled language. And of course, by the time you submit the proposal, not all the code transformation has been completed. Now, and that is perfectly fine. And so you just do scaling tests on the most time-consuming parts, and you just explain a little bit how that works. So that is perfectly perfectly fine. Yeah, and the last sentence particularly important. We would make sure that we've optimized the best possible this most time-consuming part of the code. Yes, absolutely. That's what you write in your proposal, and you convince the reviewers that you are on a good track, and so on and so on. And of course, when your code is not production ready, you will not ask for all the production that you have in mind. You of course have to keep in mind that you say, I get an award for a year, and for the first 6 months, I do some more code development and testing, and in the later 6 months, I do my first production computation. So keep that in mind. Apply common sense when you think about how many SUs you are asking for. But that is of course perfectly fine. We always encourage people to improve their codes, and you are not being dinged by the reviewers for that. Oh, the question from Johnny, I do not fully understand. It seems clear that the kind of processes on the x-axis, communication versus worker, doesn't make much difference. I mean, when you present the scaling, usually you present the scaling for the whole thing, that is communication or computation. But of course, if you have, you know, what I have on my slide here, additional considerations too, if you have made a detailed analysis that compares what your scaling looks for the communication part and what your scaling looks for the computation part, you should also put that in. That is very impressive work, and reviewers will appreciate your effort, that you delved into the different characteristics, you know, the characteristics of different things that your code does, communication and computation. And then of course you are throwing in that you do asynchronous communication, where you try to hide as much of the communication while computation is being performed, and so on and so on. So always when you do something extra, or you dive into details of your code, reviewers want to read that. It assures them that you know what you're doing and that you are interested in improving your code. And of course, when you look at this, at your scaling, if you look at the performance for your communication, there are of course algorithms where you have all-to-all communication, and where the scaling is naturally never linear. And reviewers know that, and so you can just discuss it openly, and that is what they want to do. Oh yes, is it useful to discuss efforts of the community on community code? Yes, of course, if you can say, hey, I'm using the latest version of this community code and it has been optimized by some other group, always put that in. And if I'm reading your comment here, it was improved specifically for working on Stampede 2 or on a specific XSEDE cluster, but my group wasn't involved directly in that. Nevertheless, you made the effort to use the latest and greatest version that is optimized for that machine. So always write that. If it is not your own optimization work, then maybe you keep the description of the work a little bit shorter. You know, you don't want to take credit for, you kind of know how that works. You want to take credit that you use the best version. You don't want to take credit for the actual optimization. So if you write that openly in your description, that will absolutely help. Oh, commercial code. Yeah, if you're using commercial code, yeah, of course, there's no optimization that you can do, and very often you cannot do any analysis, but nevertheless, you do the scaling, you calculate the correct number of SUs you want to use, and basically everything applies except for the fact that it is commercial code, and sometimes, or maybe even often, you are not allowed to look into some details that it's commercial code, and you cannot modify that. But everybody will understand that too. Okay, and I think now I'm already on my last slide. Design your proposal around the computational plan. Demonstrate efficient use of the resource through scaling, and your scaling is a proxy. It's in non-ideal situation, but that's the way it is. Scaling is the easiest way to get at least some handle on what your software is doing. Add some basic math that tells the reviewer how you estimate your total SU request size. Be reasonable with your request size. Keep in mind how many nodes does a machine have, how many hours are they in a year, and think about ramping up over time. This is a fierce competition. I mean, with fierce, I mean, Ken told you that 80% of the proposals are awarded sometime, but better proposals do significantly better. There are quite a lot of proposals where the reviewers say, hey, this is a very good proposal. It provides all the relevant information. Scaling is there, everything is looking good. So therefore we recommend full allocation. That is a very, very typical review. And a little bit of effort on your side goes a long way. Let me just go back to the chat room. Yes, there's the question from Arvind about Abacus. Yes, you still have to document the scaling, because you use the scaling to also estimate the total number of SUs. Also, can we request more nodes to run jobs to do the scaling analysis? Yes, I mean, once you have your startup allocation on a resource, you can ask for as many nodes as the queue limits allow. And for Abacus, the queue limits are much higher than what you would need for your Abacus scaling, because I think that usually is at most a few nodes. Yes, I have the question from Charles. I think I have addressed that. It's from Johnny. It seems that there is a diversity of y-axis variables for the scaling plots. Are there any variables that are definitely bad? I mean, you use speed up or you use scaling efficiency. You use anything where your ideal scaling is a linear line. Either for weak scaling, it's a constant, or for strong scaling, it is kind of a linear line. And if you delve into details of yeah, no, this is true really for everything. If you separate out computation versus communication, again, you will present timings for the computation and for the communication, and just make sure that when you put it in a plot that you do 1 over the timing and not the timing itself. The timing itself, as the timing decreases, is a 1 over x relationship. So it's more like, it's this one here on the right-hand side. And that is, you can already see, that is very hard to judge. If I would tell you, oh, what is the scaling efficiency between the point on the left to the point on the right, I have to put in a lot of effort, and there's a lot of uncertainty. Okay. Yeah, how do the reviewers determine the reduction of the requested allocation? So if the reviewers are not completely happy with your proposal, there are several approaches. Sometimes they start picking at, oh, experiment A looks good, but experiment B doesn't look so good. And so they cut experiment B. Or they say, it's a parameter study, but I don't really know, I'm not convinced that they need 50 points in the parameter space to begin with. Let's give them time so they can do 20, and then I want to read how that informs their selection of the next of additional points. And then, of course, at the very end, there is, of course, a cut of all awards so that the awarded time matches the total available time. And that is kind of a general haircut, but again, there are different factors that are additionally accounted for. So proposals that do not have funded science behind it, NSF funded or NIH or DOD, get a higher cut than the science projects that are funded. Also, larger requests, the haircut is higher than for smaller requests. And on the other hand, on the other side of the coin, there are special rewards that reviewers can give out. So they can, for example, say, oh, this is an excellent proposal and they do everything right, but they need really the time, the whole time that they have asked for to answer this question, and they can recommend to put the proposal in a no-cut category. So after all the awards are tallied, then those proposals are exempt from the haircut at the end. Yeah, thank you. Okay, we still have a lot of time. Keep the questions coming, and I try my best to address them all. Oh yeah, there's a comment from Bob. Yes, Science Gateway's proposals are handled differently and often exempt from allocation cuts. Yes, PI eligibility. I mean, Ken is much better, much in a better situation to talk about that. But if you are at a US institution, you are eligible once you have your PhD. Then there are few programs where you are eligible without being having a PhD. But for unaffiliated individuals, Ken, maybe you can unmute and weigh in.
Yeah, so I've been following these questions. So I did point Ali out to the XSEDE allocation site. There's a section there about policies, and there is a subsection of the policies about eligibility. So our understanding is that anybody affiliated with a U.S. Institution, and it doesn't have to be an academic institution, it can be a government lab, and it can also be a company. But if it is a company, your science has to be made public. Nothing can be proprietary. So, and even we have individuals that have eligibility. You know, they are an adjunct professor or something. They have had a long-standing career in a field or so. So, if you have some concerns or questions, what I'd say is, why don't you send an email to help@xsede.org? That's the best place for any questions about anything in XSEDE. And I would be happy to have a discussion with you in detail by phone or email. It would be fine. So Ali, hopefully you go ahead and do that, and we can dig into this a little deeper. And any other questions others may have, feel free to send those as well.
Thank you. I'm looking. I do not fully understand the question from Charles. In scaling experiments, what is the appropriate number of replications of each number of nodes to use? That maybe, Charles, if you can elaborate a little bit, or maybe, I mean, if we all stay disciplined, Charles, if you want to unmute and ask a question that way. Oh, Bob sent me a private chat that it is maybe getting the variability in runtimes. Oh no, so of course you run your scaling experiment, and unless you suspect that some of your experiments suffer from high variability, you only run the test once. If you, unless, I mean, you do not want to waste a lot of SUs on these experiments. And with waste, I mean, you have only a limited number of SUs from your startup, and you have to use them wisely to get through all the scaling that you want to document. And so unless you think there's a lot of variability, you run it only once. Yeah, I'm not sure if there will be more questions, but maybe I can wrap up by saying that we will expand this slide deck and this talk to cover also other areas like AI and machine learning and things like that. And we will repeat this presentation frequently. So if you have colleagues who have questions about how this all works, please, tell them that there's a resource that they can use. Yes, there's a question. If only one system was requested for a startup allocation, how do we go about requesting to test other systems? Yes, you can ask for supplement for your startup, but in many times, very often that is not necessary. If you have a startup on a cluster in Pittsburgh, and now you want to request time on a cluster in San Diego, then you can look at the architecture of the cluster, and you can see these are all, no cluster gets very old in XSEDE. So the architectures are very often comparable, and then you can make an argument that, hey, we tested it on Comet, and now we want to use the cluster in Pittsburgh, and you can work around that. But if you feel that you need absolutely testing on the targeted system, then ask for a supplement. And as always, keep in mind that if you have a smaller request, then any fudging with, oh, my scaling is not absolutely on the system that I'm targeting, will be more forgiven than if you put in a really large request. So common sense, as always, applies. Okay, Ken or Jay, one of you want to wrap up, or how do we proceed?
Sure, Lars. Hey, I appreciate you giving the talk. Very informative. Had some great questions. Folks, if you think of some other questions along the way, again, feel free to send email to help@xsede.org. If I can't answer them, I will get them to Lars, and if Lars can't answer them, we'll find somebody. The ECSS staff is happy to help and answer questions. We'll be happy to follow up on this. I believe Jay says we will be able to send the slides to everybody on the registration list. We also recorded the session, so we will be making this available on a site here shortly. And I think it was a good first time, so I think we're good to go. Again, questions, send them to help@XSEDE, and we'll be happy to get answers back to you as quickly as possible.
Yeah.